Hello, welcome to Advanced Composites. Today is the fifth day of the ongoing week, which is the ninth week of this course. Last 3 days, we have been discussing the principle of virtual work and how it can be used as a powerful method to solve problems related to deflections in composite plates, where the analytical solution may not necessarily be either available or it may be non-obvious. Today we will continue this discussion and we will solve the problem in context of a beam, but here we will not have just one term solution but a multiple term solution, and we will see how we can have multiple that is a series solution for deflections, and we will illustrate it through the example of a beam which is isotropic and pinned at both ends or simply supported at both ends. So we will generate the solution for a beam for two-term solution. So if we know how to do two-term, we can do it 3 to 4-term or whatever. So we will generate a two-term solution, and once again the beam is simply supported on both sides. The beam axis is at the center. So this is my x axis, this is my z axis, and I am interested in finding out the deflections for the beam. The beam is again experiencing a uniformly distributed normal load, which is q newtons per meters or q naught newtons per meter. The length of the beam is L, so this is minus L over 2 and this is plus L over 2. What are the boundary conditions? The boundary condition is that W is equal to 0 at this end, and also the moment is 0 at this end, and W is 0 at this end, and the moment is 0 at this end, because it is simply supported on both the points. And to remind you, if we use virtual work, then we will only worry about the kinematic boundary conditions, that is boundary conditions which relate to displacement and slopes, not related, it does not relate to, or kinematic boundary conditions do not relate to forces and moments. So we will worry only about W is equal to 0 at both ends. Before we do that, okay, so what is the governing differential equation? The differential equation for the system is EI d4 W over dx4 minus q naught is equal to 0. This is the governing differential equation. We had seen this earlier, and we will say that the displacement is having two terms, A1 cosine pi x over L plus another term A3 cosine 3 pi x over L. So this, we have chosen this function. This function W is equal to 0 at x is equal to minus both plus and minus L over 2. So this function satisfies both the kinematic boundary conditions. So we are fine with this function. Okay. So this was step 1. The next step is that we have to find the error force. So error, and here it is only a function of x, is if I plug this W back into the governing differential equation. So this is equal to EI A1 pi over L 4 cosine pi x over L plus A3 3 pi over L to the power of 4 cosine 3 pi x over L minus q naught. This is the error. Oh, I am sorry, this q naught has to be outside the bracket. So, this is the error or the residue. Okay. Third, we have to write the statement for virtual work is equal to 0, and for that we have to first select a function for virtual displacement. Okay. So, virtual displacement, now here is the trick. In the function for W there are two terms. So, and what are unknowns? The unknowns are A1 and A3. So, when we choose the function for displacement, there also we choose a two term virtual displacement field. That will make things easier. So, virtual displacement is W1 x, and again we use the Galerkin method, special Galerkin method. So, we use similar functions. So, this is equal to A11 cosine pi x over L plus A12, I am sorry, A31. So, this extra subscript implies that it is virtual displacement cosine 3 pi x over L, and we have to make sure that this virtual displacement field satisfies all the kinematric boundary conditions, because this function is same as the actual displacement field, it satisfies all the kinematic boundary conditions. So, satisfies W is equal to 0 at x is equal to plus minus L over over 2. So, that is there. So, the last step is, now we say that we have to compute the virtual work and equate it to 0. So, what is virtual work? It is error force times virtual displacement integrated over the domain. So, minus L over 2 to L over 2 EI A1 pi over L to the power of 4 cosine pi x over L plus A3 3 pi over L 4 cosine 3 pi x over L minus q naught. This is the error times parameter of smallness, which is epsilon, times virtual displacement field A1 cosine pi x over L plus A31 cosine 3 pi x over L dx, and this is the overall virtual work. So, it has to become 0 as per the principle of virtual work. Now, what we do is we have a multiple of virtual work with respect to error force, and we reorganize these things. So, what I get is minus L over 2 to L over 2, and first I multiply everything inside and I collect all the parameters which are multiplied by A111. Okay. So, epsilon A11 cosine pi x over L times EI A1 pi over L to the power of 4 cosine pi x over L plus A3 3 pi over L to the power of 4 cosine 3 pi x over L minus q naught okay. So dx, so this is one integral plus minus L by 2 to L by 2 epsilon A31 cosine 3 pi x over L EI A1 pi over L to the power of 4 cosine pi x over L plus A3 3 pi over L 4 cosine 3 pi x over L minus q naught dx is equal to 0. Okay. So, I have just reorganized whatever was there in the integral into two separate integrals, that is all I have done. Now, what I will do is I will move this integral sign. So, I will take the epsilon A11 out like this, and I will do the same thing to the second integral, because A31 and A11 they are constants. Okay. And I call this entire integral I1 and I call this entire integral I2. So, essentially what I get is epsilon A11 I1 plus epsilon A31 I2 is equal to 0. Okay. Now, this relation, this A11 and A31, they are arbitrary numbers, they can be anything, they can be anything. So, for this relation to be true, the first term has to be individually 0 and the second term has to be individually 0, because A11 and A31 are arbitrary numbers, they can be anything and they are not 0. So, what that means is that I1 should be 0 and I2 should be 0, because A11 and A31 are arbitrary, they can be anything. Okay. But this equation has to be true for all values of A11 and A31. So, it can be true only if I1 is individually 0 and I2 is individually 0. Okay. Now, if you look at I1, you get basically you get an equation in A1 and A3, and if you look at I2, you get another equation in A1 and A3. Okay. So, you get two equations with two unknowns. So, basically you will get, when you solve this I1 and I2 and you reorganize, you will get a 2 by 2 equation system, and this is how it will become. Okay. So, you will have a 2 by 2 matrix multiplied by vector A1 A3, and on the right side right side you will have another matrix. Okay. So, this is called the stiffness matrix, and this is called the force vector. and A1 and A3 are amplitudes of the displacement component, right. What is the first component? First component is A1 cosine pi x over L, second component is A3 cosine 3 pi x over L. So, you solve for these and you get A1 and A3. Okay. So, all it requires is just basic arithmetic, algebra, integral calculus, and these are simple functions. So, it is not difficult to integrate them at all. So, once you do that, you get the values of A1 and A3, and the results are A1 is equal to 4 over, excuse me, pi to the power of 5 QL4 divided by EI, and A3 is equal to A1 by 35, negative of that. So, this is what we find out. So, W naught x is equal to 4 over pi to the power of 5 cosine pi x over L minus 1 over 35 cosine 3 pi x over L. Okay. So, this is our two term solution. Similarly, if we wanted to do a three term solution, what will we do? We will go back to our expression for W. We will have three terms. Maybe I will just extend this. So, I will say A1 cosine pi x over L plus A3 cosine 3 pi x over L plus A5 cosine 5 x pi over x over L. So, I will have three terms. Next, I will compute the error force. Then I will have my virtual displacement, and in virtual displacement again I will have three terms involving A11, A31 and A51, and then I equate the virtual work to get 0, and then here I have a two equations involving A1 and A3. There I will get three equations, and I solve for A1, A3 and A5, and that is how I do it. So, this is the thing, and just for comparison purposes, W naught at 0, which is the origin, is equal to 0.01302 Q naught L4 by EI. This is the two term solution, and it is 0.01309 Q naught L4 by EI. This is a one term solution, and it is 0.01302. It is Q naught L4 over EI. This is an exact solution. So, we see that in this case, just by having two terms, the midpoint, the deflection of the midpoint of the beam is pretty close to the actual value, at least up to 4 places of decimal, just by having two terms. So, this is the overall approach, and we can use a very similar approach for plates also. So, that is what I planned to do today, and we will continue this discussion tomorrow as well. Thank you.